And we have our warm-up problem, which of course, that's from last time. We have a function, f of x, which is x to the power 6 minus 15x to the power 4 plus 27x squared. And it has the property that f of negative 2 equals f of positive 2. How many values of x satisfy the conclusion of the mean value theorem for the interval between negative 2 and 2? And their options are 1, 2, 3, 4, or 5. Okay, so you've got a 1 in 5 chance, but of course, you know the mean value theorem, so hopefully it's a lot better than a 1 in 5 chance. What's the answer? The answer is C. Okay, so let's remind ourselves, what does the mean value theorem tell us? It says that there is a place where the instantaneous rate of change, and that's this part right here. This is our instantaneous rate of change, how it's changing at the moment. It has to match in at least one place to the average rate of change between the endpoints. Now there's at least one, but there can be more than one. In this case, it looks like there will be 3. Because f of 2 and f of negative 2 are the same, it's really asking the question, how many times is the derivative 0? But not just how many times is it 0, how many times is it 0 in the interval that we're under consideration? Well, we take the derivative, we can pull out a 6x, and it factors in terms of x squared nicely, and so that the roots are negative 3, negative 1, 0, 1, and 3. We don't want negative 3 and 3 because they're outside the interval. So we only take the negative 1, 0, and 1. Those are in our interval, so we have 3 roots. On a side note, it is possible to have what's known as a repeated root. What would be the count if 0 was a root twice? So say it had been negative 1, 0, 0, 1. What would have been the count in that case? Would it be 3 or 4? It would be 3, because it's still 0. Even though it's a repeated root, it's still just one place where the derivative equals 0. All right. Any questions about material from last time? Okay. Good. Well, our small thought for the day, or is it a big thought? Well, it's not. Maybe it's somewhere in between. Small changes can lead to big impacts. And oftentimes people say, I want to have a big semester. I want this to be my best semester ever. And you say, well, the only way I can do that is something big has to happen. But no. Oftentimes, small changes, very tiny things that you do, can have a huge impact. And in particular, the sooner that you make a change, the bigger that the impact is. It's akin to, say, planes. Now, planes used to fly. They still do. But they didn't used to have all our fancy technology. And so what would happen? Well, ideally, they were supposed to fly directly from A to B. But what can happen is even a small deviation, and all of a sudden, you're way off over time. So that small change at the start builds up, and it accumulates. Now, that's not how planes would fly. Well, how would they fly? Well, they would fly something along the lines of the following. They'd head off, they'd get off course, and they'd correct, and usually they'd overcorrect, and it was very zigzaggy. So this was back in the old days, like the 1950s. How do they fly now? Still want to go the same location. I still have the same straight line. Now what do the flights look like? Now they're fairly close to the line. Now they may go off a little bit. How did that happen? What happened in the intervening few decades? GPS, that helps a lot. And also computers. Computers could say, the GPS is just ever so slightly off. Let me make small corrections. And by making small corrections, it's able to stay on that nice path. What's the result? Well, we use less fuel. Airlines like that. We can also pack more planes in the sky because now they're not going all over the place. And so small changes have big impacts. Now, tomorrow is an interesting day. You may have heard about it. There's an election, and of course, all the faculty at Iowa State, we're all politically neutral, and we have no opinions about it. However, we do all want our students to vote. And oftentimes people are saying, why should I vote? I'm just one vote. I'm a small vote. I can't make a change. But I want to say that's not true. Sometimes your vote can matter a lot. And it's always important to hear how people feel about what's going on. To give you an idea of just how close some races can be, I want to go back in time to about when you were roughly the same height you are now. 4 years ago, there was a U.S. Congress seat race in Iowa, so not far from here. There were 400,000 votes. Well, there were about 396,000 votes, but there were almost 400,000 votes cast. What was the margin of victory? What do you think?
200?
6. Now, this is from Wikipedia. I didn't make these numbers up. You can go look online. 6 votes separated the winner from the loser. The person who went to Congress and the person who did not go to, I don't know what they did afterwards, but that's not that much. To give you an idea of how small that number is, there are more than 6 people in this room. So votes matter. So I encourage you, if you are eligible to vote and have not already done so, please take some time to vote. All right, so that's that. Okay, on to today. Well, I should have split this up over many slides, so I'm just going to sort of throw a lot of stuff here and ramble for a bit. But the good news is you have handouts. So what's today? Well, today we're talking about the antiderivative. A lot of people cling on to the anti part and say, yes, at this point in the semester, I am very much anti-derivatives. I don't want to see another derivative. Well, unfortunately, I should warn you, they're going to keep coming. But now, when we talk about anti, it's not necessarily means that you're against. Anti here is in the sense of it's the opposite of. So not opposed to, but the opposite. So the antiderivative says, I want to do whatever the opposite of the derivative is. And so we say that a function, capital F of x, is an antiderivative of little f of x if you take the derivative of little f of x, you get, the derivative of big F of x, you get little f of x. So somehow, it's almost like you ran the machine backwards. When I talk about the machine, it's the derivative machine. So we have this derivative machine here. Imagine I could write with small letters. And normally we throw in a function, and out comes a different function. Well, now the question is, suppose you know the output is f of x. What did you put into the machine? That's the goal of antiderivatives. What did you put into the derivative so that you got a particular function out? So it's almost like we're trying to do an inverse operation. Now there's a couple of notes. You might say, okay, so suppose I succeed. How many antiderivatives will I get? Well, the answer is there's basically one or infinitely many, depending upon how you feel. But there's this notion of unique up to a constant. And we learned this from the last lecture. We said, hey, if 2 derivatives match, then the original functions basically just differ by a constant. So if you found one antiderivative, you have found all antiderivatives as soon as you add a plus c. Now, what is c? Well, c is, in some sense, it can be whatever you want it to be, but oftentimes we'll use it to be a particular value. So we might say, oh, there's additional information that we have to satisfy. That additional information tells us which value for c we should choose. All right. Well, notation. We have notation for taking derivative, so we should have notation for taking antiderivative. And so we will, and it's this symbol here. So our old notation for derivative, our new notation for antiderivative. And you might say, that's an interesting choice. Why that? Well, spoiler alert, we're going to be sort of talking about derivatives in antiderivatives in a couple of different ways. So there's something called an integral, and an antiderivative is called an indefinite integral. So you might say, so there's a definite integral. Yes. And that's what we'll start talking about, I think, next time. But, okay, so where does this come from? So essentially, the way I like to think of it is that this part right here is take the letter S and put it on the rack so that you're stretching. So it's an S that's been stretched out. And why do we stretch out the letter S instead of any other letter? Well, spoiler alerts, S for sum. And we'll talk about why that makes sense later on. We'll also have a dx at the end. Again, this will make more sense once we get into definite integrals, but notationally, it's very important. Get into the habit of writing it. And I know that notation is like, notation, smotation, whatever. But once you get to, say, Calc 3, you're like, oh, notation is very important, and I'm going to be very careful with my notation. And because notation does matter. Okay, a few other comments. We're going to develop these ideas for antiderivatives. Now, it sounds like that's going to be a lot of work. And the answer is no. It's going to be very short. It's actually surprisingly quick. Why? Because we know derivatives, and they're connected. So once we have rules for derivative, they become rules for antiderivatives. Oh, well, that sounds like it's going to be fun. Because at this point in time, we have all these cool rules for derivatives. We can basically take the derivative of anything. You give us a function you can write down. It's like, yeah, here's its derivative, no problem. But when we go to antiderivatives, it turns out it's challenging. And if you don't trust me, find someone taking Calc 2 and ask them. Because that's what you get to do for a good chunk of Calc 2 is learning how to integrate. And why is it challenging? Well, for derivatives, like I said, you give me a function, I can tell you its derivative. For antiderivatives, I can do about 10. There's about 10 functions I can find the antiderivative for. And that's it. That's it. 10. And you're like, wait, what? That seems like you can't do a lot. But here's where it gets fun. You see, maybe I only have 10, but I can modify what I have. So most of the game when it comes to doing antiderivatives or indefinite integrals or definite integrals boils down to saying, I can't do very much, but maybe if I keep rewriting, keep thinking of ways to express this in a simpler way, I can get to something that's in my list of 10. And that's how the game goes. All right, so that's a pretty quick summary, but pretty good. Any questions about antiderivatives? Just the philosophy behind it. All right. Well, let's get into some rules then. So if we want rules for antiderivatives, where should we look? Rules for derivatives. All right, well, so I wrote down a bunch of rules for derivatives. Now, what are they? I haven't written down all the rules for derivatives. And we're going to add to our list here. But these are the ones to start us with. Now, the first rule that's written down, this is actually a really cool fact. And this part right here is what we call the property of being linear. So it says that if I'm adding two functions, taking the derivative, I can separate the derivatives and do them independently. If I have constants, I can pull constants out. So the linear part is our way of saying, oh, I can pull a big thing if it's being added into lots of little things. So that's the rule for derivative. And what's going to happen is, since derivatives are linear, then we're going to get something nice about our antiderivatives. So what does it become? Well, it says that the integral of a f of x plus b g of x dx is a integral f of x dx plus b integral g of x dx. So you can break up over addition. If you can break up, you can also smush together. That's also allowed. It's nice. It goes both ways. Okay, so that's our first rule. And this is probably one that gets used most often, and it's used so often that we don't think about it. But it's important to state it. Okay, so one other generic rule. It's a very special case of the chain rule. So here I'm thinking of capital F as being the antiderivative of little f. And I say, suppose I take the composition. So I have kx plus L is the function on the inside of this big F. Well, that's a function in a function. So if I have a function in a function, what rule am I using? Chain rule. So it says take the derivative of the outside. That's where the little f comes in, because this is the antiderivative. Leave the inside alone, times by the derivative of the inside. Okay, so what's the corresponding rule for antiderivatives? It says if I want to integrate, and I have little f of kx plus L dx, where little f, I know how to take its antiderivative. I'm assuming here little f has the antiderivative of big F. What will that equal? Think of the rule. And essentially you can think of integration undoes both sides. So think about integrate both sides. What do you end up with?
Capital F kx plus L over f, or over k?
Capital F of kx plus L, yep. Over k. So I'll put a 1 over k in front. Now the nice thing is, k is a constant. And there's one basic philosophy. Constants are easy to move around. Why are they easy to move around? Because of linear. You can move things, constants in, you can move constants out. Now, is there anything else that we should put down? Plus c. All right. So we're going to keep writing down plus c many, many times. Okay. Good. All right. Well, then we have 8 basic functions. You might have said, wait a second, you mentioned 10, Steve. I did mention 10, but we'll do 8 today. Okay, so which one do you want to start with? Okay, we'll start with the first one then. Okay, so the derivative of x to the k is kx to the k minus 1. So, based on that, what is the integral of x to the power k? So just think of here, you subtracted 1. What's the opposite of doing a subtract 1? You should add 1. Anything else that we need?
1 over k.
Okay, so we should have a 1 over. What did you say? K. Interesting. It's k is close. It's k plus 1. Now, what else? Plus c. How can you check if your antiderivative is right? Is there a way to check?
Take the derivative.
Take the derivative. And so if in doubt, take the derivative and see if you end up with the right function. So if you took the derivative of x to the power k plus 1, what would you end up doing? Power comes down. The k plus 1s cancel. And then it'll be just 1 in front. X to what power now? K. So the derivative of this is x to the k, which means this is the right antiderivative. So when in doubt, take the derivative and see, am I getting back what I started with? Okay, so now, next one. The integral, so I'm trying to look at the output. So the integral of 1 over x, what will that be? ln of x. So if the output of the derivative is 1 over x, the question is, well, what did you put in to get 1 over x? How about integral of e to the x?
Wouldn't it still be e to the x?
It's e to the x plus c. Okay. Do you see where these are coming from? We're putting our outputs into the antiderivatives, and then these are going in modified as needed. What's the integral? 1 over 1 plus x squared dx.
Tan x plus c.
Arctangent of x plus c. How do we get that? Because we see it. We see the output was 1 over 1 plus x squared. So the output from the derivative, if I'm looking at that, well, then I should have arctangent of x. All right. We still have 4 to go. So what's the integral of cosine of x?
Negative sine x plus c.
So integral of cosine will be sine. So this is, it's one of those things where it's like, it's weird. Okay, before we say it's weird, let's do the integral of sine. What's the integral of sine? There's this negative. But what can we do with negatives? Negatives are like constants. So we can move them. So the integral of sine is negative cosine. So this is one of the things where people often make mistakes, because it's kind of the opposite of derivatives. So the derivative of sine is positive cosine. Now the antiderivative of sine is negative cosine, so you have to be careful. Keep track of your signs. We saw the signs, and we don't want to lose any points. We saw the signs. Okay, we have 2 left. What's our next antiderivative going to be of?
Secant x.
Well, so if we're doing an antiderivative, we have to have something that came out. So it's going to be one of these two. I can tell you what the antiderivative of secant x is, because that's one that's not on the page. So secant squared x. What's the antiderivative of secant squared x? Tangent x, because the derivative of tangent gave you secant squared, so the antiderivative of secant squared going backwards is tangent. Plus, of course, constant. Antiderivative of secant x tangent of x. What would that be? Secant x plus c. Do you want to see the two other ones that I haven't put on? Or do you just want to wait and do it organically? All right, so the other two integrals that you'll need to know to get you from here to the end of differential equations. The integral of tangent, because that's not on our list. Does anybody know this one? Right, it's log secant. Good. And the integral of secant x. Anyone know this one? Log secant plus tangent on the inside of the log. So these are the 10 antiderivatives that you should know. For now, focus on the 8 to start with. Everything else, our goal is to say, can I make it look like one of those things right now? Okay, so any questions? Because the rest of today is mostly practice after this point. All right. I see a question. Good.
So the first integral you took for x to the k, when you're writing the integral sign, wouldn't it be k x to the k minus 1? Because you wrote x to the k dx.
It is true that you can say the antiderivative of kx to the k minus 1 dx is x to the k. But in terms of how we think about antiderivatives, it's more convenient for us to say, I want to express it as, what's the antiderivative of x to the k? So we sort of anticipate, like, in practice, how do we want to think of it? All right. Well, let's do a simple warm-up. Okay. Don't worry, we're doing this one together. It's a group activity. All right, so the goal is find the antiderivative of 7x squared plus 4 over square root of x plus 2x to minus 1 plus sine of x plus 6e to the negative 2x plus 1 over 1 plus x squared plus e squared dx. Okay, what's the first thing that we can do? Yeah, people, I heard the word separate, I heard the word pull it apart. See how we have all these plus signs? These are good plus signs. Now you might say, is there a bad plus sign, Steve? Okay, I'll point out there's a bad plus sign. This is a bad plus sign. Why is that a bad plus sign? It's downstairs. Things downstairs are hard to deal with. Things upstairs, woohoo, break it apart. Things downstairs, Okay, so one thing we can do automatically is pull it apart. So instead of thinking about it as like this big, like, we can think about it as a bunch of little, in sequence. Okay, you don't have to make the noise when you're doing it, by the way. Okay, so after practice, you'll probably just write the answer down without even thinking about it. But let's go through. So 7 integral x squared, we'll come back, plus 4 integral. Now 1 over square root of x. That's not very calculus to write 1 over square root of x. So what do we do instead? X to the negative a half. Why write it in this way? Well, because our rules. You think of how the rules are written. The rules are written as x to a power k. So you say, okay, I really want to get x to the power k. So I don't want to use the square root symbol. I want to use notation that matches the rules. Plus 2, there is an exception to that rule. How should we write x to the minus 1? 1 over x. That's the exception. Why? Because we have a special rule for that one. All right, plus the integral sine of x dx plus 6 integral e to the minus 2x dx plus the integral 1 over 1 plus x squared dx plus, now, what do we do with this e squared? What is that? It's a constant. Okay, so if we pull it out, we just have e squared integral dx. Is that okay to write that? Does integral of dx mean something? Well, think about it for one moment. Take 1 second to think about what it could be. So the integral of dx just means you're integrating 1. So you're integrating 1. So that's okay. So you can say that. All right. Well, now we'll just go through in order. Okay. So apply the rule. What's the integral of x squared? By the way, I will often say integral instead of antiderivative, because that's how people speak. So, add 1 to the power. What's our new power? 3. And then what do we do? Divide by 3. So put a 1/3. Plus 4. X, what's our new power? A half, because we're going to add 1. Negative 1 plus a half. Sorry, negative a half plus 1. I can say these words. Is a half. And then we're going to divide by a half. Well, how do you divide by a half? Multiply by 2. What's the integral of 1 over x? The log. What's the integral of sine? Is it negative cosine or positive cosine? Yeah, it's negative cosine. Yeah. Don't worry. I'm just making you check. Okay, now we get to one that's interesting. The integral of e to the minus 2x. How do we handle that? Do we have the technology for that? I claim we do. So what rules do we need? Well, we know how to integrate e to the x. But what do we have? We have e to the negative 2x. Well, that's like you have a kx plus l, where k equals minus 2 and l equals 0. So e to the minus 2x is into the side of this category. So when we take the antiderivative, it's like you just take the antiderivative as before, but leave the inside alone, but divide by what's in front of the x term. With all that said, think of just integral of e to the x. Integral of e to the x?
E to the x.
E to the x. So this is going to be integral of e to the minus 2x is e to the minus 2x. And then there's a correction. And the correction is to account for the minus 2. So what else do we need? Need to divide by negative a half. Or divide by negative 2, which is the same as multiplying by negative a half. So this here is k equals negative 2, 1 over k. How are we doing? We're almost there. What's the integral of 1 over 1 plus x squared?
Arctangent.
Arctangent! Yeah! Booyah! That's the coolest! I'll tell you, there are people in this department who are just in love with the arctangent function. Maybe there's just one. But there's a lot of love towards arctangent. It's a great function. You'll see it a lot. Okay, what's the integral of e squared? Yeah, e squared x. So it's that constant times x. All right, is that it? Plus c. Now wait a second. We just did 1, 2, 3, 4, 5, 6, 7 integrals. Shouldn't we have like 7 constants? Is 1 constant enough? Why is 1 constant enough? I mean, I agree with you. I'm not saying that I'm not trying to challenge you, but let's understand why 1 constant is enough.
Because a constant can be anything, so one constant can also be 7 constants.
Wow, a constant can be anything. Sounds like a pep talk. One day, you too can be president of the United States, Constant, if you try hard enough and campaign in Pennsylvania. Okay. But I like your thinking. A constant can be anything. The way I like to phrase it is that constants are like sponges. And what that means is you can absorb other constants. So if you have a constant, which can be anything, when by that we mean any number, and another constant, which can be any number, if you have 2 arbitrary numbers added together, the result is an arbitrary number. So an arbitrary constant plus an arbitrary constant, just say, look, put them together. And so you only need 1 constant at the end. So that's the answer, but just for fun, I would just clean it up a little bit. So 7/3 x cubed plus 2. And if you want to go back and say, I like square root notation, that's fine. 2 squared of x, or 2x to 1/2, 2 log of x, minus cosine x, minus 3 e to the minus 2x, plus arctangent of x, plus e squared times x plus c. See, not so bad. Antiderivatives, they're easy. All right, good. Now that we've had our warm-up, should we do another? Yep, let's see. Do 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 do. Do 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 do. Okay. Find the integral of 1 over 1 plus sine theta. Okay, that's not so bad. Is it on our list? No. Okay, that's bad. Because we need things that are on our list. So what do you do if it's not on the list?
Change it.
Change it. Yes. So you start saying, are there ways to rewrite this? Well, any ideas? What can you do with the 1 plus sine theta?
Make it 1 plus sine theta to the power of -1.
Okay, well, that's certainly one way. Do you have a game plan after that?
Working on it.
Okay, all right. It's not bad. Now, the good news is that's a trig function. And I say, why is that good news? There's trig identities. Now, the bad news is there's a lot of trig identities. So sometimes it's hard to know which one to use. But there's a few trig identities that you should know by heart. Is there any trig identity where you have, say, 2 things being added on one side, but not on the other side? So somehow you can get rid of addition.
Should we multiply by conjugate?
Oh, well, yes, we should multiply by the conjugate. Okay, so spoiler alert, we're heading towards the conjugate. Because sine squared theta plus cosine squared theta equals 1 is a thing. We like that thing. It makes us happy. Now you might say, well, how does the conjugate relate to that? Well, let's find out. So we have, this is the same as integral 1 over 1 plus sine, multiplied by 1 minus sine, over 1 minus sine, d theta. And upstairs we have 1 minus sine theta. When we multiply by the conjugate, 1 plus sine theta times 1 minus sine theta, what does that become?
Would it be 2 plus sine theta minus cosine theta? No.
Well, won't be that complicated. It's like a plus b, a minus b. So when you think of conjugates, a plus b, a minus b, 1 minus sine squared. Now, this one you're like, I know factor 1 minus sine theta as 1 minus sine times 1 plus sine and cancel. Ha ha ha. No, that's getting us back to where we were. That's not making progress. That's going backwards. But is there a way to think of 1 minus sine squared? Cosine squared. All right. Well, hey, what can we do here? Now, previously, what did we have? We had a bad plus sign because it's downstairs. Now what do we have? We have a good minus sign. Why is it good? Because it's upstairs. So what does that allow you to do? Separate as two things. Now, 1 over cosine squared, does that have another name? Secant squared. Does secant squared make us happy? Why does secant squared make us happy? This is a happy occasion for us. But why? Because it's on our list. We know how to take the integral. Yes, it's on our list. Being on our list is a happy thing for us. With that in mind, sine theta over cosine squared theta, can we write that in some way that makes us happy? Our list is short. Someone mentioned tangent. How do you get a tangent from sines and cosines? A sine over a cosine, but that leaves us with a single cosine left. So if we had a tangent, we'd still have a 1 over cosine, which is secant. So this is like secant tangent. Does that make us happy?
Yes.
Why does it make us happy? It's on our list. Now, it's all happiness. Double happiness. Okay, so what is the antiderivative of secant squared? Tangent. What's the integral of secant theta tangent theta? Secant. Is that our answer? Plus C. Get in the habit. Add your C. Add your C. All right, well, let me talk about one other concept before we finish, because we have about 6 minutes or so. And this is the kind of thing they like to ask. So we know a couple of things. We know if you take the derivative of the position function, you get velocity. If you take the derivative of velocity, you get acceleration. So we've done problems in the past where we said, hey, let's start with position and get to acceleration. But can you go backwards? Can you start with acceleration and find position? Well, almost. You have to have some information. So the information comes in what are called initial conditions. So the initial conditions tell you what's happening at various points in time. Usually they at time 0, but they don't have to be. And we can use that to figure out the constants that will arise. Because when we go from acceleration to position, we're going to have to take 2 antiderivatives. That means 2 constants. So use initial conditions to solve for the constants. So here's a problem. This is based off of an exam problem from a while back. And there's a longer story. There's a manager at a paper company, and he's doing a presentation. And the manager's name is Michael Scott. And he has drones. He calls them Scott's bots. Okay, so the controls for Scott's bots are not working. The acceleration is fixed. So the acceleration is 2 minus 6t, so they can't change the acceleration. T happens to be measured in minutes from the time you turn it on, which is at time 0. Now, for the presentation, we need to have the position and the velocity have to be 0 at time t equals 2. What should be the position and the velocity at time t equals 0? All right, so let's figure this out. We know our acceleration is 2 minus 6t. How do you go from acceleration to velocity? You antiderivative. Usually we say integrate. So what is velocity at time t? So what's the antiderivative of 2? 2, what's our variable? T. So it'll be 2t. Antiderivative of 6t. It'll be probably a t squared. What's the coefficient? 3. Good. Anything else? Plus c. Now, what's our initial condition? Right. At 2, velocity is 0. So that says 0 equals v of 2. That's the initial condition for velocity. Well, let's plug in 2. 2 times 2, 4. Minus 3 times 2 squared. So minus 12 plus c. So 4 minus 12 plus c has to equal 0. So what does that tell us about c?
C is equal to
Negative
-8.
8? I think it's positive 8.
Yeah, positive 8.
All right. So now we can update. We say, cool. So our real velocity function is 2t minus 3t squared plus 8. Now let's go to position. I think we use S for position. All right. Take antiderivatives. Antiderivative of 2t. T squared. Antiderivative of 3t squared.
3t.
Well, it'll be t cubed. What's in front? It'll be 1. It's 3/3. Antiderivative of 8? 8t. And I should add, solve for constants soon in the process. Because you might have said, well, I'll first do my 2 antiderivatives and then I'll solve for c. Solve for c early. Okay, what else do we need? Plus a constant. Well, we've already used c. Good news is the alphabet is big. So we'll move up to the next letter, plus d. You're like, oh, thank goodness. We only ever need 2 constants. Well, just wait until you get to diffie q. And we have problems where we get up to the letter r. Good times. Good times. I'm looking forward to the adventure. All right. Now, again, position at 0 at time 2. So we get that 0 is s of 2, which is 4 minus 8 plus 16 plus d. So what does that say about d? So d is negative 12. Okay, so our position is t squared minus t cubed plus 8t plus d. Finally, just let's finish it up. The question was asked in a very particular way, the velocity and the position at time 0. Okay, so velocity at time 0, what does that turn out to be?
8.
Is 8, and if they corner us, we say it's 8 yards per minute, because we know how to work with units. Units always work out. What's your position?
-12 yards.
Negative 12 yards. All right, that's it for today. Have a great day.